calculating the pH of a weak acid. Now, you remember that weak acids only partially ionize in solution, and that distinguishes them from strong acids which virtually completely ionize in solution. So what does that actually mean on the atomic molecular level? Well, here we have a weak acid. This is acetic acid, which happens to be the acid that's in vinegar. And when you put acetic acid in water, most of the acetic acid stays in the molecular form. Only every now and then does one of the protons, what we call the acidic proton on the acid, actually ionize and release a free proton and acetate ion into the solution. You can tell that only a few of the products form because of the equilibrium constant Ka. It's 10 to the minus 5, which is far less than 1. Since it's far less than 1, reactants are favored, and in this case, the reactant is an intact molecule of acetic acid. Now, when you're given the initial concentration, in this case, 0.15 molar of the acetic acid, and you're given the equilibrium constant Ka, you can calculate the hydrogen ion concentration using the technology that you've learned called the ICE table, which stands for initial concentration, the change that takes place when the reaction proceeds, and then the equilibrium concentration that results after a sufficient amount of time has elapsed. So the initial concentration in our problem is 0.15 molar of acetic acid. We don't have any products to start, and that's hydrogen ion and the acetate ion. Our change is going to be minus X, consistent with our coefficients, and plus X for our products. And then we simply add the initial line in the ICE table to the change line, and that gives us 0.15 minus X. 0 plus X is simply X. 0 plus X is simply X. Now, the next step, I always recommend students who skip this step invariably have more errors than students who complete this step each time. It is your choice, but I do recommend that you write the equilibrium constant expression. Now, you'll notice that instead of writing acetate out, I'm using the generic weak acid designation of simply HA, A minus standing for acetate. It's simply a lot simpler, more convenient, and faster to do it that way. And all of these anions are the conjugate bases of the acetic acid, and A minus and HA work very well for us. So the next thing I have to do is I have to make a decision about how much math I want to do. And I don't know about you, but for me, the less math I actually have to do to get a reasonable solution, the better. So I'm going to look at two things. I'm going to look at the initial concentration of the acid, which is 0.15, and then I'm going to look at the equilibrium constant, which is on the order of 10 to the minus 5. This equilibrium constant is very small with respect to this initial concentration. In fact, the initial concentration is far more than 1,000 times larger than the equilibrium constant. And considering that, what I can say is that reactants are so favored that the X value, the degree to which ionization of the acetic acid, in this case, takes place, is going to be very, very small, which means this X is going to be very small, and at equilibrium, I'll have very close to my initial concentration. Now, don't be confused. X is not 0, so I can't ignore these X's. I'm simply making a choice to ignore the X with respect to the initial concentration. Once again, because Ka is 1,000 times smaller than the initial concentration. And you can determine that by simply dividing Ka into the initial concentration, and if it's 1,000 times smaller, then you know that you're probably safe in making the simplifying assumption that that X is small enough to ignore. Okay, so we're going to ignore that when we do this math. So here we go. We've got the Ka, which is 1.8 times 10 to the minus 5 is equal to x times x, which is simply x squared. And because I'm making the simplifying assumption that the x relative to the starting concentration is small, I just have to put the initial concentration of the acetic acid 0.15 in the denominator. I'm going to go ahead and solve my problem by taking the Ka, which is 1.8 times 10 to the minus 5, and I'm going to multiply it times 0.15, and that's going to equal x squared. Now, I could go ahead and calculate that result. I actually prefer to do that in my calculator and take the square root at the same time. So I'm going to go ahead and take the square root to get rid of the x squared term and take the square root of this product. When I do that, I get an x value that's equal to 1.64 times 10 to the minus 3 molar. And that's important to remember that this is actually the concentration of the hydrogen ion for this weak acid once it reaches equilibrium. I can calculate the pH of the solution by simply taking the negative log base 10 of the hydrogen ion concentration, which is going to be equal, in this case, to 2.79. Now, that's the pH. I do have one other step that I always want to include. I want to verify that the percent ionization of my hydrogen ion, this is called percent ionization, is equal to less than 5% of my starting concentration. And so all I have to do is to calculate that is take my x value, which is 1.64 times 10 to the minus 3, divide by my starting concentration of my acetic acid, which was 0.15, multiply by 100, and indeed I get a percent ionization of 1.1%, which is far less than the 5% rule that I have for assuming that the x relative to the initial concentration is small. Always perform this. Make sure that your assumption is a valid assumption. And there is our pH.